All right, good afternoon, physical science. Hopefully, you guys are starting to study and get ready for your exam coming up next week. Remember, exams start on Tuesday. So, Tuesday will be 1 2, Wednesday 3 4, Thursday 5 6, and then Friday 7 and 8. Periods that you do not have a class, like lunch or study hall, you do not have to come for those exams. Okay? But if you have a class, you need to make sure you are there. Okay? So, going back over some of the key concepts from motion. Remember, we know an object is in motion if it changes its position relative to a fixed location. So, if you're sitting in your chair right now, relative to the desk, you are not moving. But if I pick a different object, like I pick the moon, we are moving relative to the moon. So even if I'm laying on my bed or sitting in a chair, technically the earth is revolving and it's rotating at the exact same time. So it rotates every 24 hours and then it revolves around the sun every single day for 365 days. It's continuous. Okay? So we said the main difference then between distance and displacement. Distance is going to be your entire path that you walked. Okay, so we just add all the legs or the entire distance that you drove. So for example, I drove from my house to Bradley today, and I'm going to drive back to my house. The distance that I drove would be 10 miles plus 10 miles, makes my 20 miles. Whereas the displacement would be relative from where I started to where I ended. So displacement is going to be final minus initial position. Well, if I started at my house and I ended at my house, then my displacement would be 0. Okay? So in this next picture, when you're looking at your walk from your house to A to B to C, and then D got cut off down here, so I added it. So if you're watching the video, you're going to see that I added that D. So from home to A, if I walked from home to A, I covered a distance of 0.5 kilometers. So my distance and displacement are the exact same because I didn't turn, I didn't do anything different. I just walked in a straight line. Well, when I want to go back to B, I'm going to turn around. So the moment that you turn around or you change your direction, your distance and displacement are no longer equal. So it was 0.5 kilometers to A. So then going back to the house is another 0.5 kilometers. So from A back to B, that would be an additional 0.5 kilometers. So add those two together. That's how you get a distance of 1 kilometer. For displacement, though, I started at home and I finished at home. So if I start and end in the exact same place, my displacement is 0. If you notice with the 0, I just included 0 kilometers, but I did not add a direction. Displacement should have direction on these. When I then walk to C, so I've already walked 1 whole kilometer, but going to C, that's going to be an additional 1 kilometer. So my total distance walking to C, from home to A, back to B, and then to C, is going to be a total of 2 kilometers. If I compare, though, where I started, which is home, to where I finished, though, I am only straight line distance from start to end, 1 kilometer from where I started. And I use the designation of E for east. You could have said 1 kilometer towards C if you would like that as well. The last part, I did add D down here. So you notice in the chart, if you're looking, there's a D right there as well. They're going to walk an additional 1.75 to the left or 1.75 to the west. So now I'm going to take that 2 kilometers and add it to the 3.75 kilometers for a total of, 1.75 to the 2 makes a total of 3.75 kilometers. In terms of displacement, though, for the displacement, I'm going to consider where I started to where I finished, which is this way. So one thing I just noticed on my key, this bit is 1 kilometer. So this little segment right here is 0.75 kilometers. So if I started here at home and I finished here for D, I would actually be 0.75 kilometers to the west, because I would be 0.75 kilometers away from where I started. All right, distance time graphs. So remember, with distance versus time or position versus time, we are looking at how fast you are driving. So how fast you're driving describes your speed or velocity depending upon how it's used. So for a displacement versus time, that slope, delta x divided by time, is going to be velocity. If it is distance versus time graphs, then that's going to represent speed. Okay? So when I look from A to B to C to D to E, remember on displacement time or distance time graphs, anytime there is a curved line represents an object accelerating. If it's a linear line, then it is going to be at a constant speed. So from B to C, that is a linear line. From C to D, though, it is horizontal. And if I look closely, C is at position 9. D is still at position 9. So if I'm at 9 meters and I'm still at 9 meters, have I walked anywhere? And hopefully you guys are saying no. So distance covered from C to D would be 0. So when I'm going away from start, I'm going to have a positive velocity. When I'm going back to start, I'm going to have a negative velocity. So there are the answers for you to check. So again, if it's position time, like I had mentioned, position time, we're leaning more towards velocity. If it's distance time, a little bit more towards speed. Can you get distance, displacement, speed, and velocity all from the same graph? Yes. Okay. The steeper the line, the faster they are going. So A is going faster than B because it's a little bit steeper of a line. Calculating speed. Speed is distance divided by time, whereas velocity is displacement divided by time. So if I go back to the graph and I want to calculate speed from B to C, well, I would have to say how far did I walk and then how far did I run. So the rise over the run, if you guys can see it right there, I rose 3 and then I ran 9. And I went approximately 9. I know it looks like it's just ever so slightly before there. But I did 3 divided by 9, which gave me the 0.33. So yours might just be slightly off depending upon if you rounded or not. For average speed over the whole trip, I need to take the total distance. So the total distance divided by the total time in order to get speed. So I figured out segment by segment by looking over here at the displacement and saying, well, I started at 0 meters and now I'm at 6 meters. So I walked 6 meters. Then here I walked 3, here I walked 0, and then here I walked 5. Remember, with distance is always going to be positive. You cannot walk a negative distance. And then the total time, I would have to read that x-axis. I got 24 seconds. So I solved and I got 0.58 meters per second. For average velocity, I need the total displacement, delta x, divided by time. So I came back up here and I said, well, I started at 0 and I finished at 4. So I need to take the final minus the initial. So 4 minus 0 gives me 4. Still going to take me the same time, 24 seconds. So my answer is going to end up being 0.16 meters per second. Now I'm going to put a positive sign there because I did end up further away from where I started, right? I ended up 4 meters away in the positive direction, even though I was heading back home. So I gave it a positive 0.16 meters per second. Okay. All right, on this next one, velocity time, it's really important that when you're looking, you read the y-axis first. So I know here my initial velocity is 0. Well, if my velocity is 0, that means I'm stopped. And then all of a sudden, I'm going 8 meters per second. So in my head, I should be saying, okay, well, if I was going 0 meters per second and now I'm going 8 meters per second, the only way for that to happen is for me to speed up. Okay. On the graphs, we also have a horizontal line. Does not mean that it is stopped now. A horizontal line means here I'm going 8 meters per second. Here I'm going 8 meters per second. So if I'm going 8 meters per second, 8 meters per second, 8 meters per second, I'm going at a constant speed. D to E is also going at a constant speed, but it's not going as fast, okay, because it's only going 4 meters per second. In terms of whether an object is going to accelerate, remember acceleration occurs when you speed up, slow down, or change direction. So even if I'm in a roundabout going 20 miles per hour and I'm going in a circle, I'm still changing my direction every single second. So I am accelerating even if the speed on my speedometer is the same. Okay? For the motion diagrams, for them speeding up or slowing down, remember, if they're speeding up in a positive direction, I want the distance between each of our snapshots. So each of those pink dots represent a snapshot. That's where that person, that car, the bike is every second. So if it's speeding up, I want to make sure that the distance between those dots increases. If it slows down, then the distance between those dots is going to decrease. Whereas if it's going at a constant speed, like for C, you're going to notice that the distance between each of those is exactly the same. Okay? All right, so that was everything for motion. I highly, highly suggest filling out using your note cards from when we made the note card for distance time, displacement time versus velocity time graphs. So you have it. Okay? Next up was forces. Forces occur when there is a push or pull. A force is the reason why we see the observed motion, why a car is able to speed up, why a person falls, or why an object falls towards the center of the earth. All of its motion is going to be caused by a force. So with forces, the first Newton's first law, an object at rest stays at rest, an object in motion stays in motion unless acted upon by an outside force. So inertia is typically referred to as the law of inertia. So remember, inertia is a property of matter. And so since it's a property of matter, anything that is matter, which is pretty much everything except for the light or the heat or the sound that you hear from me right now, they're going to have inertia. Inertia does not resist motion. It resists changes in motion. So once a semi is going 70 miles per hour on the freeway, it wants to keep going 70 miles per hour on the freeway. Okay? The more mass it has, the harder it is to change what it's currently doing. So speeding up, slowing down, a semi is going to have a harder time than a smaller car. Okay? Then we had free body diagrams. So if you take a look down here, I'm going to start here. When I'm trying to decide if they are balanced or unbalanced, I'm going to look left, right. Are they the same number? Yep, then they are balanced. Look up and down. Oh, that one's not the same number, so this must be unbalanced. Okay? Whereas here, I'm going to look left, right. Those are the same. And I'm going to look up, down. Those are the same, so those must be balanced. Remember, when I have an unbalanced force, that is going to cause an object to accelerate. Okay, so it's either going to speed up or slow down or change directions, right? And it will always do that in the direction of the motion. Okay, so if the object's speeding up or slowing down, then I know the forces are unbalanced. If the object is going at a constant velocity or is at rest, and then the forces are balanced. Okay, so remember, balanced forces have no net force because they end up canceling each other out. Usually up is positive, down is negative, so a positive 2 plus a negative 2 cancels out. A negative force, negative 5, and a positive 5 are going to cancel each other out as well. Remember, friction always opposes motion. So if the car is coasting to the right, remember I'm not pushing on the gas anymore, but it's coasting to the right. But friction is to the left. And so that friction isn't going to make the car actually move to the left like most typical forces. It's just going to slow down the car. Okay? So there are your answers for that chart. Remember, with F net equals ma, F net equals ma, if I exert a greater force, the object is going to accelerate a little bit faster. If the object has more mass, it's not going to accelerate as quickly. When you're using F net equals ma, remember m stands for your mass, a stands for your acceleration. So on 17, you're just going to go ahead and take your 1,000 and multiply it by your 3. Force is also a vector quantity, which is going to allow for us to identify how much force and in what direction that object will accelerate. So the acceleration will also line up with the net force. So if it's accelerating to the right, then it's going to be a net force to the right. This one did not include a direction on the acceleration, so I went ahead and I treated it as a positive. So when I gave my final answer, I said positive. Okay. F equals ma was Newton's second law. Newton's third law, which is number 18, is for every action, there is an equal and opposite reaction. So if I am looking at a bat striking a ball, the ball then also strikes the bat. So we have forces acting on two separate objects, but those forces are going to be equal in magnitude. I always ask students, I say, well, which force is greater? They always want to say the bat force is greater because the ball goes flying. Well, the ball goes flying because it has less mass, so it has less inertia. So it requires a smaller force to get it to accelerate. So we would actually have those objects moving. They both experience the same force, but how they move, the resultant effect of that force is not always the same. Okay? So some of the forces that we had tension, friction, applied, gravity. Another name for gravity is weight. Air resistance, and then normal would be the last one. So we had 6 different forces that we had talked about. With the force due to gravity, yes, objects can have different weights, but they all are going to accelerate towards the center of the earth at 9.8 meters per second squared. So the acceleration is always going to be the same. So if I take 2 objects, drop them from the same height, they will always strike at the exact same time, unless if we have a lot of air resistance. If there's a lot of air resistance, then that's going to change it, and the net force is not just going to be the force due to gravity. So if there is a lot of things that are different shapes, like a feather and a hammer, that feather is not going to land at the same time as the hammer because it's just going to kind of float back down. Float, float, float. All right, work and energy. Remember, in order to do work, you have to exert a force over a given displacement. So exerting a force and the object has to move. All right, so remember, I might push on the wall. I might hold a barbell above my head, but unless if I don't move it, then I'm not going to be doing work in the physics sense. Okay. With kinetic energy, EK or KE, either or. And then gravitational potential, remember that was PE or GPE. They each have separate equations. So kinetic energy is 1/2 mv squared. Potential energy is mgh. So depending upon what variables are in that equation, they're either going to increase or decrease or have no direct impact. Okay, so you can see those answers there. All right, 22, I forgot to fill this in for you. Law of conservation of energy states that energy cannot be created nor destroyed. Now, it can transferred forms. So I can go from potential to kinetic, back and forth, back and forth, back and forth. So when I look at this one with the ramp, if I set the ball at the top and I'm just holding it there, I don't have any kinetic energy. So I have all potential. So it has the potential to roll down that ramp. So once it starts rolling down, the height decreases. And as that height decreases, the potential energy goes down. And you would remember, if you think back to our lab, the ball or the car is going to start to roll faster once you get to the bottom, because we're going to have maximum potential at the top and then maximum kinetic at the bottom. The exact same thing can be said about a pendulum. So with the pendulum, we're going to have max potential at the ends. So if you look A and G, those are max potential. And then maximum kinetic, where it's moving the fastest, is when it has no height above that starting position at D. So the higher I raise that wrecking ball, the faster it's going to go at the bottom. Okay. A couple ones there was solving. If I know total energy is 2,000 joules, that means if you look at the circled objects above on the ramp, at position 1, 2, 3, 4, and 5, I'm going to have a total of 2,000 joules of energy. So halfway down at 3, I have 1,000 joules of potential and 1,000 joules of kinetic, always adding back up to be that 2,000. Okay. So if I look at this in perfect world scenario, I should have all potential at the top and all kinetic at the bottom, and they should be equal to each other. But in reality, we have friction, right? And so friction is going to take that motion and it's going to oppose it. And when it opposes it, then that causes the object to lose some energy. And I don't say lose because we can't destroy energy, but they lose energy in non-mechanical forms. So like heat, sound, light. Okay, the most common one is going to be heat or thermal energy. All right, again, like a reminder, I said at the beginning, work equals force times delta x. Work equals force times delta x. So I need to have a net force and I need to have a displacement in order for work to be done. If the object does not move or if it is balanced forces, then no net work. Okay. Thermal energy, as we get into these last 3 final units, these were smaller units. We're not going to have as much content on the exam as the first 3 units that we had talked about. So you want to make sure that you're keeping an eye on that and spend a little bit more time going over the first 2 units. Okay. Remember, temperature measure the average kinetic energy of the particles. This is kind of a sensation, whether it feels hot, whether it feels cold. Objects that are good conductors, whether that's thermal or electrical, they can heat up quickly in terms of thermal, or they allow electrons to flow through it in terms of electrical sense. For those that do not heat up quickly, that would be an insulator. Remember, we talked about water. Water is a good thermal insulator because it takes a long time for water to heat up, but water is a good conductor of electrical energy. So it can actually, you can get electrocuted with water. So electricity flows through water, which is, why you got to be careful. You can't blow dry your hair while sitting in the bathtub at the same time. That would be really dangerous. Remember when it's raining outside, if you're standing in a puddle and there's lightning and stuff like that, you got to be careful with that too. Remember, we have conduction, convection, radiation. Conduction is our actual direct contact. So when I sit down in the chair feels cold. Well, my body transfers heat to the chair, and that transfer is going to continue to happen until they reach the same temperature. Convection occurs because we have fluids and gases that rise and fall based upon differences in densities. Then radiation is our only one that can travel through a vacuum or out in space. The faster something melts, the better conductor it is. The slower something melts, the better insulator that it is, because it's not allowing for that heat to move through it very quickly. Okay. Next unit, waves. Biggest things, remember, there are different types of waves. We can have transverse, we can have longitudinal, we can have mechanical, or we can have electromagnetic. Okay. So a wave is just a disturbance that moves through space or matter. Mechanicals do require a medium, whereas electromagnetic do not. Transverse, the particles move perpendicular, whereas longitudinal, they move parallel. Okay, the 2 different looks of those waves, so how they look, transverse is the typical wave where you have the up and the down, whereas with longitudinal, you have more so movement side to side, where parts of the spring are compressed and then parts of the spring are relaxed. So since mechanical requires a medium, they're going to move fastest through a solid. Electromagnetic does not want a medium. They are going to move fastest in a vacuum. So don't forget those 2 with speed. Speed is not determined by the height of the wave. Speed is not determined by frequency. It's not determined by wavelength. It is strictly determined by what material it's going to move through. Okay? Some of those definitions again: refraction, that's the broken straw or pencil in a cup of water. It's a bending of a wave because you're entering a new medium. Reflection is the bouncing back, so echoes, sonar, echolocation, things like that. Diffraction, that's the bending of a wave as it goes around a barrier or through a gap, so people can hear me in the hallway even though they can't see me. Interference, when those two waves interact, it can either make a larger or smaller wave, constructive for the bigger one, destructive for the smaller one. The Doppler effect would be that apparent change in frequency because the observer or source is moving. So the ambulance, as it comes closer to you, sounds a lot higher pitch, higher frequency. As it moves away from you, the waves are starting to spread back out and it sounds lower pitch, lower frequency. Now, the sound actually being produced by that ambulance is not actually changing. It's just an apparent change. It's something that we think we notice, but it's not the same. All right, electricity, that's our final unit that we have covered on the exam. Remember, opposites attract, likes repel. Remember, batteries use chemical energy to create a potential difference between the positive and the negative terminal. Electrons build up on the negative terminal and flow towards the positive terminal because, again, opposites attract, likes repel. Once we hook up a battery in a circuit and we use wires and we can use a light bulb, all that good stuff, electricity is going to start to be produced. Electrons are flowing. The voltage, think of that as how hard those electrons are being pushed. The harder they get pushed, the faster they move. So that is measured in voltage. Current is how fast or how slow they're moving, measured in amps. Resistance would be the amount of our resistance to the flow of electricity. Unit would be ohms. V equals IR. Remember, V is voltage, I is current, R is resistance. So increasing voltage makes the electrons move faster. If the material has a greater resistance, then it's going to cause the electrons to move a little bit slower. Okay? And we had said conductivity resistance kind of goes hand in hand. If it's more conductive, then it has less resistance naturally. If it is less conductive, then it has more resistance. For series versus parallel, remember we had built some of these. With series, there's one hooked after the next after the next. If one of them goes out, they all go out. The current, because there's only one path for the electrons to move, is going to be the same across each resistor or each light bulb. Whereas with parallel, we have multiple paths for those electrons to travel. And so if one burns out, they can keep moving in those other paths, so everything else keeps working. And since they're hooked individually to the battery, the voltage is the same. All right, after going through that, if you have any more questions, please make sure you are reaching out so I can help you get ready for that final exam, and it will be summer before you know it. All right.